So let's start with few more circuits. Now the circuits that we will discuss today can be made only through capacitors. Like up to last class, the circuits that we have discussed were similar for both capacitor as well as resistor, but the circuits that we will do today can be made by using capacitor only. These circuits are not possible using resistors. So if you take just one more thing, to analyze these circuits, we will use this simple trick that in series combination, charge stored in each capacitor is same. Charge stored in each capacitor is same. And just one more thing, if two capacitors are in series, then say this is the positive plate, this one is negative plate, this is positive plate, and this is negative plate. So in series combination, negative plate of one capacitor is connected to the positive of another. So the type of circuits that we will do today, to analyze those circuits, just keep this thing in mind that in series combination, negative plate of one capacitor is connected with positive of another. So negative plate of one capacitor and positive plate of another capacitor are connected, that's series combination. While in parallel combination, the positive plate of one capacitor is connected to positive of another. If I say that capacitors are in parallel, that means positive plate of one capacitor is connected to positive of another. So this means positive of one capacitor is connected to positive of another. So this is how we do parallel combination. Series combination, positive and negative plates are connected. For parallel combination, positive, positive and negative, negative are. So the first circuit based on this capacitor. Say you have some plates given in this form. So you have few plates which are given in this form. The area of each plate is A and the separation between each plate is B. This is separation between the plates. You're supposed to calculate equivalent capacitance. These are very important type of questions on capacitors. So in these type of questions, first of all, you have to count the number of capacitors. How many capacitors are there? To count number of capacitors, just try to remember what was the condition to make a capacitor. To make a capacitor, you need two plates which are oppositively charged. I'm repeating it again. The condition to make a capacitor work, you need two conducting plates which are oppositively charged, separated by a dielectric medium. If you have two plates having same charge, similarly charged plates, it's not a capacitor. For capacitor, both the plates should have opposite charge. So to decide the number of capacitors in this problem, Say, let's provide positive charge to this plate. Positive charge to this plate. Similarly, this plate will get positively charged. Give negative charge to this plate. So this will get negatively charged. The total number of capacitors are 3. See, this is positive plate, this is negative plate. This positive and negative will make one capacitor. This negative and this positive will make another capacitor. This positive and this negative will make third capacitor. The answer, when you say 4 or more than 3 capacitors, you try to combine this plate and this plate. This and this plate does not make a capacitor. So this is one capacitor, this is two capacitor, this is third capacitor. So total number of capacitors 3. Because once you have counted this as a capacitor, then you can't say that this plate and the last plate will also make a capacitor. And you can't say that this positive and positive plate can make a capacitor. The reason is the polarity of charge on both the plates of capacitor is different. So these are total 3 capacitors. Is it clear? Now we can calculate capacity of each capacitor, C1, C2, C3. All are parallel plate capacitors. So the capacity is epsilon naught A by D. All 3 capacitors have capacity of epsilon naught A by D. C1, C2, C3 is epsilon naught A by D. We need to calculate C equivalent. C equivalent is the sum of C1, C2 and C3. C equivalent is epsilon naught A by D plus epsilon naught A by D plus epsilon naught A by D. So here C equivalent is 3 epsilon naught A by D. So this is the equivalent capacitance, rise of epsilon naught A by D. This is the equivalent capacitance of the system. Okay, just solve this question. The question is same, you're just supposed to calculate the total capacity of the system, equivalent capacity. So again, to solve this, just provide positive charge to this plate. So this whole will become positive. Can you count the total number of capacitors now? Afroza, how many capacitors are there?
2.
2 capacitors, very good. This positive and negative plate will make a capacitor. But since these 2 plates are negative, it's not a capacitor. These one positive and negative plate will make a capacitor. You have total 2 capacitors. Okay, one more thing. So you have 3 capacitors, C1, C2, C3. Now you have to decide the type of combination. I missed that explanation. You have to decide the type of combination, whether these 3 capacitors are connected in series or they are connected in parallel. To decide the type of combination, we proceed by the method of charges. If all positive plates are connected at one place and all negative plates are connected at another, that means your capacitors are in parallel. Say for this first capacitor, positive plates, I call this plate as P and this plate as Q. Fatma, at which point the positive plate of first capacitor is connected?
P.
P, very good. And where is the negative plate of first capacitor? Where is this negative plate of first capacitor connected?
Q.
Q. Where is the positive plate of second capacitor connected? Positive plate of second capacitor. This one. This is again connected at P, right?
Yes.
And where is the negative plate connected? So you can check. See, this is the negative plate, this is negative plate, and it's going up to Q. The negative plate is connected at Q. Where is the positive plate of third capacitor connected? See, this is the positive plate and it's going up to P. And the negative plate is connected up to Q. So we can say that all positive plates are connected at P, and negative plates are connected at Q. So all positive plates are connected at P and all negative plates are connected at Q. If all positive plates are connected at one point and negative are connected at another, what's the type of combination of Rosa?
Parallel.
This circuit can be simplified as this. So you have this combination, three capacitors connected in parallel. That's why I have written that C equivalent is C1 plus C2 plus C3, and this is P epsilon of V. Padma, is it clear now?
Yes.
Sure. In this second question, you just have two capacitors. If all positive are connected at one point and all negative are connected
Parallel.
parallel, very good. The positive plate of first capacitor is at P, second is at P, negative is at Q. So if you have capacitors in parallel, then C equivalent is simply C1 plus C2. That comes out to be 2 epsilon naught A by D. This is the equivalent capacitance, 2 epsilon naught A by D. Next question. Say you have a parallel plate capacitor, and in this parallel plate capacitor, in between the plates, I filled a dielectric of some dielectric constant. The dielectric constant is plate area separation is D, plate area is A. So, Jubana, what is the capacitance of the system?
K E epsilon
Right.
A by D.
K epsilon not A by D. Okay, let's modify this numerical somehow. Now, instead of one dielectric, let's fill two dielectrics. So, let's fill two dielectrics. Plate area A, separation D. This is K1, this is K2. So, the first dielectric occupy the half area, the next again occupy the half area. It's A by 2 and A by 2. You're supposed to calculate the equivalent capacitance of the system. So you can write C1. C1 is K1 epsilon naught A by 2D, and C2 is K2 epsilon naught area is again half, it's A by 2D. So you have two capacitors. Now to combine them, you need to know how these two capacitors are connected, whether they are connected in series or in parallel. So this is your first capacitor, right? This red one is your first capacitor, that yellow one is your another. To decide whether these two capacitors are connected in series or in parallel, just give charge to each plate. Make one plate positively charged and another negatively charged. One positively charged and another negatively charged. Can you decide, Fatima, how these two capacitors are connected? This is this red one and this yellow one. Series or in parallel?
Parallel.
Why? Why they are in parallel?
Because all the positives are in one plate, connected to one plate, and the negatives are connected to another.
So these two are in parallel, right? Since positive is connected to positive and negative is connected to negative, these two capacitors are in parallel. The simplified is this one. This is C1 and this is C2. So your C equivalent is C1 plus C2. So your C equivalent is K1 epsilon naught A over 2D plus K2 epsilon naught A over 2. C equivalent is epsilon naught A by 2D K1 plus K2. This is C equivalent, epsilon naught A by 2D, K1 plus K2. Next question. We again take the same parallel plate capacitor. Let's fill dielectrics in this way. Instead of dividing separation, they divide, instead of area, they divide the separation between the plates. So area is A, area is A. Here separation is d by 2 and separation is d by 2. Dielectric constant K1, dielectric constant K2. This is it. You have to calculate the equivalent capacitance of the system. See now again you have two capacitors. C1 is K1, epsilon naught A. The separation between the plates is d by 2, so it's d by 2. It comes out to be 2K1 epsilon naught A by D. And for the red capacitor, you can write that your C2 is K2 epsilon naught A over D by 2. So that's 2K2 epsilon naught A over D. And this boundary will itself act as a plate. This boundary will act as a plate. This boundary is acting as a plate. So if I start providing charge, if I give positive charge to this plate and negative charge to this plate. So due to this negative charge will get induced at the boundary and a positive charge will induce on the opposite side. I'm repeating it again. You have two dielectrics, K1 and K2. So the point at which these two dielectrics separate each other, this boundary of separation will act as a plate. So if this plate is positive, a negative charge will get induced over this plate and a positive charge will induce this boundary. Negative will induce here and positive will induce. So Afroza, can you guess what type of combination is this? Is it series or is it parallel?
Series.
Why they are connected in series, Afroza?
Because it's positive and negative are connected together.
Right, because positive and negative are connected together. So they are connected in series. So if they are connected in series, you can write your C equivalent. You would calculate your C equivalent in this way. 1 by C equivalent is 1 by C1 plus 1 by C2. Okay, just substitute the values and get the final result. So yes, 1 by C equivalent is, it's D by 2 K1 epsilon naught A. Let's say it's D by 2 K2 epsilon naught A. So 1 by C equivalent is, you can take this D by 2 epsilon naught A as common. It's 1 by K1 plus 1 by K2. So 1 by C equivalent is, it's D by 2 epsilon naught A. Here LCM is K1, K2. It's K. So your C equivalent is 2 epsilon naught A K1 K2 by D into, this is how we calculate C equivalent. The series combination. Now, the next type of circuits are in both the chapters. These circuits are in chapter 2 as well as chapter 3. So they are known as Wheatstone bridge. You can make Wheatstone bridge with capacitor as well as resistor. So whatever we are doing for capacitor here is equally valid for resistors as well. So see, this type of combination is known as Wheatstone bridge. So this is first capacitor C1. This is second capacitor C2. This is third capacitor C3. This is fourth capacitor C4. And this is the fifth capacitor, which is C5. This particular combination of 5 capacitors or 5 resistors is known as Wheatstone bridge. The special thing about Wheatstone bridge is there is no capacitor which is connected in series or in parallel. There is nothing in series or in parallel. You can't solve this circuit using normal series and parallel combination. So no capacitor in series or in parallel. There is not a single pair which is either in series or in parallel. So these circuits cannot be solved using the usual methods of series and parallel combination. But there is one condition in this type of circuits which is known as balancing condition. Balancing condition. If your bridge is balanced, if bridge is balanced, balanced bridge means potential at P and potential at D are equal. VB is equal to VD. This is true if your bridge is balanced. If your bridge is balanced, that means no charge will store. See, if bridge is balanced, then potential difference across C5. Potential difference across C5. If you calculate potential difference across C5, which is V5, V5 is VB minus VD, which comes out to be 0. If it is balanced, that means there is no potential difference between B and D. V5 is 0. If V5 is 0, that means charge stored in C5. Charge stored in C5, which is Q5. Q5 will be CV, will be 0. So balanced bridge means potential at B and D are equal. Potential at B and D are equal, that means potential difference across this capacitor C5 is 0. Potential difference across C5 is 0, that means no charge stored in C5, Q5 is 0. So this is what we mean by balancing condition. But the issue is, how would you identify whether potentials are same or not? This is fine, that balancing condition means potential at B is equal to potential at D. Potential difference is 0. Charge stored in C5 is 0. But the question is, how would you identify that whether your system, your Wheatstone bridge is balanced or not? To identify whether the bridge is balanced or not, we use simple case. If bridge is balanced, then using all these conditions, we can derive this. If bridge is balanced, that means the ratio of C1 and C2 is equal to ratio of C3 and C4. This is the balancing condition. If your bridge is balanced, then the ratio of C1 and C2 is equal to C3 by C4. This is the balancing condition of Wheatstone bridge. That is C1 by C2 is C3 by C4. If you can satisfy this condition, that means charge is 0, potential difference 0, potentials are equal. Now, if your bridge is balanced, that means no charge stored in this C5. If no charge stored in this C5, that means this C5 is not making any significant contribution in your circuit. You can simply remove it. I'm repeating it again. If no charge is stored in C5, that means this C5 is not making any significant contribution in your circuit. You can simply remove it. The C5 is doing nothing here. So you can just remove your C5. So this is your cell of EMFE. Here capacity is C1. Capacity is C2. Capacity is C3. Capacity is C4. This is A. This is B. This is C. And this is D. Now this circuit is easy. Giovanna, can you guess which two capacitors are connected in series now?
C1 and C3.
C1 and?
C3.
Not C1 and C3. There is branching.
Sorry. C1 and C2 and C3 and C4.
Yes. C1 and C2 in series. C3 and C4 in series. And combination in parallel. Now this is a solvable circuit. C12, this is C3. So when you have combination of 5 capacitors and you can't find series and parallel combination, then once check the given circuit may be Wheatstone bridge. If it is Wheatstone bridge, then check the balancing condition. If it is balanced, then you can remove this C5 and these two, you will get pairs of series and parallel combination. But if this circuit is not balanced, then it cannot be solved using the usual methods of series and parallel combination. To solve this circuit, you need a Kirchhoff law. Yeah, Fatma. We would know that V5 is 0 using this equation. If this equation holds that the ratio of C1 by C2 is C3 by C4, that means potential difference is 0. I'm not deriving this result right now. We will derive it in chapter number 3. Chapter number 3, this derivation is in your syllabus. So I'm not deriving it right now, we'll derive. But for the sake of numericals, if this condition holds, that means these all conditions hold. Q5 is 0, V5 is 0, VB equal to. This is the EMFE. This is 5 microfarad. This is 10 microfarad. This is 1 microfarad. This is 2 microfarad. This is 3 microfarad. I call this as C1, this as C2, this as C3, this as C4, this as C5. So first of all, you have to decide whether the circuit is this Wheatstone bridge is balanced or not. To check whether this bridge is balanced or not, just take the ratio. C1 by
Yes, sir, it's balanced.
balance, yes, 1 by 2. Similarly, C3 by C4, it comes out to be 1 by 2 again. So C1 by C2 is C3 by C4. Means bridge is balanced. If this bridge is balanced, then you can easily remove this C5 from it. The C5 is not making any contributions, just remove it. So this 5 and 10, this is C1 and this is C2. This is C3 and C4. See, C1 and C2 are in series, C3 and C4 are in series, combination are in parallel. So C1 2 is series combination of 5 and 10, which is 5 into 10 by 5 plus 10, which is 50 by 15, which is 10 by 3 microfarad. Similarly, C34, 1 into 2 by 1 plus 2, it's 2 by 3 microfarad. And this combination C12 and C34, they are connected in parallel. C12, C34 are in parallel. So you can write your C equivalent as C12 plus C34. So that's 10 by 3 plus 2 by 3, 12 by 3, which is 4 microfarad. You can apply the same concepts to resistor also. So you have resistor of 5 ohm, you have resistor of 10 ohm, you have resistor of 1 ohm, you have resistor of 2 ohm, and you have a resistor of 3 ohm. Calculate equivalent capacitance, equivalent resistance. Check whether this bridge is balanced or not. If it is balanced, then you can remove 3 ohm and get the final result. R1, R2, R3, R4. So R1 by R2 is 5 by 10, which is 1 by 2. R3 by R4 is 1 by 2. So R1 by R2 is R3 by R4. Bridge is balanced. If bridge is balanced, then you can remove this resistor. I'm removing it. R1 and R2 are in series. Then R12 is 5 plus 10, which is 15 ohm. R34, 1 plus 2, which is 3 ohm. R equivalent is parallel combination. So that is R12 into R34 by R12 plus R34. So your R equivalent is 15 into 3 by 15 plus 3. R equivalent is 45 by 18. 9592. 5 by 2. Yes, it's 2.5 ohm. Different forms of Wheatstone bridge. Like you can modify numerical a little bit. Different forms of Wheatstone bridge. So this is the standard Wheatstone bridge. You can make it using a capacitor or a resistor. That's purely your choice. Let's make it using a capacitor. This capacitor is C1. This capacitor is C2. This is C3. This is C4 and this one is C5. This is point A, this is B, this is C, this is D, and this is C. Okay. See, just by modifying these wires, you can transform this circuit into various forms. Like one of the possibilities is this. One of the possibilities is this. This is C1. This is C2. This is C3. This is C4. This is C5. This is point D. This is point D. This is point A. And this is point C. It's the same circuit. The same circuit. The simple transformation that instead of these slant lines, I take a straight line. That's it. The next modification could be, instead of these straight lines, I can make it curve. If I make it curve, then it will look like see, this is C1. This is point A. This one is point B. This is C1. This is point C. This is C2. This is point D. This is C3. This is C4. And this is C5. These are the same circuits. We can do one more modification. Like we can push this point D upwards. I'm just pushing this point D upwards. So if I push this point D upwards, the circuit will look like if we push this point D upwards, like this is point D, this is point B, this is point A, this is point C, this is C5, this is C1, this is C2, C3, C4, and this is the cell. This is the cell. So it's again the same circuit. I just have pushed this point D a bit upwards. So these are few modifications of the Wheatstone bridge circuit. You can have one more modification. You can even make this as so this is point A, this is point C, this is point B, and this is point D. So this is C1. So in between A and this is in between A and D, this is B, this is B, this is C1. Between B and C, this is C2. Between A and D, it's C3. Between D and B, it's C5. Between D and C, it's C4. Again, a form of Wheatstone. So these are questions that were asked in CBSE exams earlier. So all our Wheatstone bridge, if they are balanced, then the method of solving is same. Now this circuit, these all circuits are basically this one. The method to solve is same, exactly same. Just note it down that this was the last circuit that we were supposed to solve.